A very good morning to all. My name is Kirti Jain and I am a research scholar at the Department of Computer Science, University of Delhi, India. Currently, I am exploring epidemic dynamics in contact networks. In this session, I will be presenting my work titled Modeling Behavioral and Epidemic Dynamics in Social Contact Networks. So I will begin with a brief introduction along with the research contributions and then present my methodology and results for each contribution. So how can math help in an epidemic? These mathematical models are basically set of equations that capture the complex reality in a simplified form. Mathematical epidemic models help us gain a deeper understanding of how diseases spread within a population. Such statistical models help us understand about how diseases spread and predict what will happen in future. For example, they can help us prepare for things like surges in demands of ICU beds and ventilators, or particularly help in exploring what might happen under various policy scenarios. So there are two common modeling approaches: deterministic compartmental models and the stochastic network-based models. Compartmental models are valuable tools for understanding disease spread. They have limitations when it comes to representing real-world complexity, variability, and stochasticity. On the other hand, stochastic network-based models are defined on graph structures that represent the relationships or the interactions between nodes. Such a model can be used to simulate the spread of infectious diseases where individuals transmit the disease to others. Stochastic elements might include varying the contact rates, probability of transmission, and individual behavioral choices. Epidemic spread is influenced by a complex interplay of various factors. The degree distribution of a network, clustering, average path length between individuals, and centrality affect the potential for disease spread. The mode of transmission strongly influences how a disease spreads. For example, diseases transmitted through respiratory droplets may have a different transmission dynamics compared to sexually transmitted diseases. Also, the duration for which an individual is infectious is a critical factor. Human behavior, including compliance with public health recommendations such as wearing masks, hand washing, and social distancing, can also influence the rate of disease spread. The widespread vaccination can significantly reduce susceptibility in a population. Quarantine of infected individuals and exposed contacts can break the chain of transmission and slow the spread of disease. So these factors are interrelated and can significantly affect the course of an epidemic. The following research gaps highlight the important areas where further investigation is needed to enhance our understanding of epidemic dynamics. So human behavior is a critical determinant of epidemic spread. Factors like fear of disease, cultural and social norms, and compliance with public health measures can significantly influence the success of interventions. So researchers can benefit from a more nuanced understanding of these behavioral factors and their integration into epidemic models. Many real-world networks exhibit community structures where the individuals within the same community have more interactions with each other. Modeling the collective behavior and interaction within these communities can provide valuable insights into the dynamics of disease spread. Moreover, real-world contact networks are influenced by demographic factors, population densities, and spatial heterogeneity. Researchers should aim to incorporate more realistic contact patterns into epidemic models. And simulating the epidemic spread on large networks can be computationally expensive and resource intensive. So research should explore efficient computational techniques, optimization methods, and parallel processing to overcome these challenges. So closing these research gaps will enhance the accuracy and applicability of epidemic models, making them more effective tools for public health decision making and preparedness. Our research contribution addresses the critical gaps in epidemic modeling. In the first research, we explore the dynamics of social behavior within different cultural contexts, specifically tight and loose cultures. Our novel framework bridges the gap between the individual fear and epidemic dynamics. Secondly, we focus on understanding the collective behavior within communities and study how these interactions influence the disease spread. We also introduce a framework that enables the creation of modular contact networks based on census data. Our research leverages the census data to model contacts within family, social, and workspaces. At last, we exploit the topological properties of the contact networks and employ the regression chain model to systematically assess the influence of network properties on epidemic variables. Each of these contributions address the key facet of epidemic dynamics. Our first significant contribution revolves around the intersection of fear and epidemic dynamics. So epidemics, whether they involve infectious diseases like the flu or more recent challenges like COVID-19, are not solely driven by the biological properties of the pathogen. While the transmission characteristics of a pathogen are undoubtedly important, human behavior plays a pivotal role in how these diseases manifest and spread within individuals. So the objective of this exploration is to examine the interplay between fear, culture, and epidemic dynamics in order to enhance our understanding of how these factors collectively shape the spread of diseases. We propose an individual-based fear model denoted by IBFM that explores the complex relationship. Culture and social events play a profound role in shaping human behavior during epidemics. IBFM acknowledges this by capturing the impact of cultural norms and societal influence on fear and behavior. We extend and use the concepts of tight and loose cultures that refer to the degree of strictness, conformity, and adherence to social norms within a society. IBFM stands apart by offering a fine-grained representation of human behavior. It achieves this by modeling fear as a continuous variable, by acknowledging that fear can vary in intensity and these variations matter in shaping the individual behavior. The model captures the dynamic adaptations in behavior over time influenced by fear and epidemic progression. IBFM also recognizes the heterogeneity in individual responses to fear. The probability of an individual getting infected is a function of two critical factors: the base transmission probability of the pathogen and the fear level of the individual. Within the framework of the individual-based fear model, several heuristics play a pivotal role in shaping the representation of human behavior during epidemics. At the onset of the epidemic, the population possesses an initial level of fear, which is influenced by the cultural norms and societal influences. A normal distribution is a common choice for modeling such responses because it allows for a range of fear levels, with most people having a moderate level of fear that is around the mean, while some individuals may have very high or very low levels of fear. When an individual becomes infected or requires hospitalization, their fear level increases. Conversely, when an individual recovers from the infection, their fear level decreases. This ripple effect extends to the individual's direct contact as well as their fear level also changes. For any susceptible individual U, the perceived risk of infection can be considered as a function of several factors, including the average fear of the population, individual fear, and the fraction of infected neighbors. For example, if the average fear is high, individuals may perceive a greater risk of infection, especially if they believe that others are also fearful. Moreover, if an individual has higher number of infected individuals, they may perceive a greater risk of infection due to their proximity to infected individuals. So the function captures the interplay of these factors. Individual transmission probability can be expressed in two forms, one with fear dynamics and another without fear dynamics. With fear dynamics, the individual transmission probability is expressed as a function of the perceived risk of infection and the base transmission probability. When no fear dynamics is considered, the perceived risk of infection does not play a role in altering this probability, and it's solely determined by the base transmission probability. We examine the impact of the initial societal fear on the epidemic dynamics. The figure shows the active cases for the 5 distinct levels of initial fear in the population. very low, low, medium, high, and very high. So without fear, dynamics implies that fear is not explicitly considered as a factor in the model. It does not mean that the population has absolutely no fear, but rather that the fear dynamics is not included in the model. We observe that without fear scenario results in the maximum peak cases, indicating a more intense outbreak, and it suggests that the fear dynamics can have a significant impact on the course of an epidemic. Furthermore, the impact of increasing initial fear levels is reflected in the shifting of the peak days to the right, indicating a delay in the timing of the epidemic peak. So the proposed model successfully captures and distinguishes the progression of the epidemic under various initial fear levels in the population. In another experiment, we study the interplay between the biological infectivity, that is the base transmission probability beta, and the initial fear in the population, and show the heat map of peak active cases. We observe that the fear and pathogen exert opposing forces on the epidemic dynamics, and their interplay can significantly impact the course of an epidemic. So very low beta indicates weakly transmissible pathogen and is less capable of causing severe illness. When the transmission probability of the pathogen is high and the fear is low, it results in a scenario where the disease can rapidly and uncontrollably spread within the population. However, changes in fear level or pathogen characteristics can bring about a significant shift in the epidemic dynamics. These results highlight the need for a comprehensive understanding of both the psychological and biological factors in managing and responding to infectious diseases outbreak. Next, we study how the convolution of the prevalence of disease and fear in the population develops a feedback mechanism evincing multiple waves of the epidemic. So the intuition is that an increase in the number of infected cases instills fear in the population while the decrease diminishes the emotion of fear. So IBFM captures this phenomena by updating the fear index of susceptible and exposed individuals based on rate of change in active cases denoted by delta computed over a time period P. So our observation reveal that periodic updates in fear levels lead to distinct and pronounced waves of infection. This observation underscores the strong connection between the population behavior driven by fear and the progression of the epidemic. To demonstrate the impact of public events on the spread of the epidemic, we decay the fear of individuals in the population. We simulate mass gathering on specific days from the beginning of the epidemic. To model the effect of mass gatherings, we incorporated decay factors denoted by lambda, which are set to three different values, 0.1, 0.2, and zero point 0.3 respectively. Figure shows the percentage increase in the number of infected individuals compared to those reported in the absence of an event. The figure demonstrates that a more rapid decay in the fear levels, as indicated by the high decay factors, accelerates the spread of the disease, which aligns with our expectations. This observation underscores the reliability of the IBFM in accurately representing changes in epidemic dynamics in response to sudden shifts in the population behavior brought about by the external events. So societies are often organized into different groups or communities, and the disparities in societal cultures and innate psychological differences may vary within communities. So the main objective of this study is to show the importance of collective behavior in terms of prevailing emotion of fear within a society that may trigger or control the disease spread, and hence must be studied critically while projecting the epidemic variables. The stochastic block model (SBM) is a statistical model commonly used in network analysis to construct network with communities. The SBM is often parameterized by the number of communities, size of each community, and the probability matrix that encodes the probability of a connection between nodes in communities. For example, consider a social network with 90 nodes divided equally into 3 communities. The diagonal values in the matrix P is the probability of an edge between nodes from the same community, and the non-diagonal values is the probability of an edge between nodes from different communities. So using SBM, we can randomly generate the connections in the network based on the probability matrix and the community structure. We show the snapshots of the epidemic spread in 5 community networks. Particularly, we consider 3 initial fear levels, low, medium and high, of the seeded community C1. Other communities C2, C3, C4 and C5 have medium initial fear levels. We infect the most central seed node in community C1 and observe that the epidemic progresses more rapidly in the first scenario, indicating that low fear levels lead to a faster spread of the disease. The high fear levels in the third scenario have a contrasting effect on the epidemic dynamics. The spread of the disease is slower compared to the low fear scenario. The experiment illustrates the pivotal role of fear in shaping the spread of the disease, with low fear levels associated with a faster progression of the outbreak and higher fear levels leading to a lower spread. In the second experiment, we show that the number of peak infections in a community-structured network is influenced both by the modularity of the network and the level of fear within communities. We observe that high modularity can lead to high peak cases. Also, the level of fear can significantly impact the number of peak infections. Higher fear levels tend to result in more proactive measures such as social distancing and adherence to public health guidelines. This can slow the spread of the disease and potentially reduce the number of peak infections. Hence, these factors collectively determine the pattern and intensity of peak infections within a community structured network. We now show that when there are substantial differences in fear level between communities, it can result in varying levels of infection spread between the communities. We model different types of community behavior by setting different initial fear levels for the 5 communities in the network. We observe that very low fear level of individuals result in faster course of the epidemic, while community with a high fear level has least number of infections. The result illustrate that the communities which comply with the restrictions, that is high fear level, also suffer the burden of the disease because of the non-compliance by other communities. The motivation for incorporating realism in network structure, especially when studying disease spread in the real world, is grounded in the need to accurately model and understand the dynamics of the epidemics within populations. Utilizing census data, which provides detailed demographic information, becomes an essential aspect of this pursuit. To address this need, we aim to develop a comprehensive framework for constructing a census-calibrated modular contact network that can be applied to any geographic area. The framework has several salient features that are crucial for improving the realism and accuracy of the epidemiological models. The framework leverages official census data, which provides detailed demographic information about a specific geographic area. This includes data on population size, household size, number of households, and the working population. The framework also adopts a modular approach to represent different zones or districts within a geography. The framework takes into account interactions that occur within family, friends, and workspaces. It is designed to handle large population sizes and is adaptable to various geographical regions. We create a modular contact network by mapping census data to the network parameters. Each geographical zone or subdivision corresponds to a module within a modular contact network. The population data is allocated to individual nodes within each zone. The population density of each zone influences the base network structure of each module. High density areas are modeled using 2D lattice, while low density areas using 1D lattice. The mean household size is used to determine the number of family contacts within the module. Larger households may have more connections between family members. The number of households contributes to the modeling of social contacts. More households may imply a greater number of social interactions within the module. The working population data is used to model work-related contacts. Individuals in the working population may have additional connections representing their workplace interactions. So we test the effectiveness of the demography-laced contact network using real-life COVID data for 3 Indian states. The selection of states is motivated by the diversity in the rural-urban agglomeration and the population density. Delhi is the capital of India and the largest metropolitan city-state with high urban agglomeration and high population density. Odisha is a large population with low urban agglomeration and low population density. Among small states, Goa has the largest urban population. Accordingly, we construct the Delhi network using demographic considerations. We also initiate the simulation on Delhi network with real data of 7 patients zone-wise as reported on 14th March 2020. We show the cumulative confirmed cases predicted by the simulation against the actual confirmed cases for Delhi. For comparison, we also construct a comparable modular network with random connectivity denoted by the blue curve. So SSCN and the SSCN RAN are comparable in the number of nodes and edges but have different contact patterns. Results show that the cumulative confirmed cases for demography-laced networks are closer to the actual curves than the random one. This bolsters our confidence in the framework and strengthens our hypothesis that mimicking social contact patterns in the wireframe is advantageous and gives better predictions. So when an epidemic spreads to a large population, early and real-time estimations of the disease infectivity are of critical importance for healthcare policy planners for managing and controlling the spread of disease. However, the cost of network-based simulations escalates steeply with the network size. This is the prime motivation to find alternatives to expensive simulations on large networks. So the objective of the study is to explore machine learning as an alternative to expensive network-based simulations to predict epidemic variables with reasonable accuracy. We generate synthetic networks of moderately large size and compute inexpensive topological features of the networks that distinctively influence the pathogen spread. We consider 3 metrics that measure the intensity of an outbreak, namely peak day, peak cases, and span. Peak cases are the maximum number of infected cases on any given day. The day when the cases are maximum is the peak day, and the span denotes the time period between the first and last infected cases. We then address the prediction of 3 epidemic variables using the regression chain model. So for this study, since no dataset is available on the internet, we curate a rich dataset. We compute 5 topological properties on each constructed contact network. Subsequently, we simulate the epidemic spread using the SEIR model and note 3 dependent epidemic variables, namely the peak day, peak cases, and span of the epidemic. Hence, we get a feature vector of 5 network properties and 3 target variables for each network. Based on the network sizes, we split the dataset into 3 partitions corresponding to small size networks, medium size networks, and large size networks. Since the epidemic variables are correlated, we use regression chain model as an ensemble built over the chain of regressors to capture the dependencies between the target variables. We set the order for the regression chain as peak day, peak cases, and span. In this experiment, we assess the competence of the regression chain model by training and testing on network properties of similar and dissimilar size networks. The matrix shows the heat map of the R2 scores and the RMSE values. The diagonal entries of the matrix shows the cross-validation results on similar size networks. For example, the first entry of the cell corresponds to the model performance when trained and tested on small sized networks. So it is clear that the cross-validated performance is quite high. The non-diagonal cells in the heat map correspond to the performance of the model on unseen data. We observe that the performance degrades marginally for the model trained on small networks and tested on large networks and vice versa. So the overall high R2 scores and low RMSE values in all cases demonstrate the competence of the regression chain model for predicting epidemic variables. Having observed that the model performance degrades for networks of dissimilar sizes, we examine the sensitivity of the predicted variable to the size of the network. We train the model using the small network dataset and test on the pool test set of large networks. We group instances into 8 batches with approximately equal number of records per batch. we observe a marginal decrease in R2 scores and a marginal increase in RMSE values for peak days and peak cases with increase in network sizes. However, R2 scores degrade notably for the span variable for larger networks, so further study is required to understand the role of the topological properties on the span variable. So this PhD work focuses on modeling realism and the development of models that incorporate social and behavioral aspects. In this context, we propose an individual-based fear model that couples the fear of the disease with the spread of the disease and demonstrates the impact of human behavior on epidemic spread. We also study the complex interplay of the collective behavior in community-structured networks and epidemic dynamics. For realistic estimates of the epidemic spread, we propose a framework for creating a surrogate social contact network that embodies the contact patterns arising from variations in population density and demography of the zones in the geography. Also, our results establish the possibility of predicting the epidemic variables using regression chain model trained on the topological properties of the contact networks. Thank you everyone for your attention, and if you have any questions, I'll be happy to answer them.